Hello everyone. I am Professor Lee from the Communication Engineering Teaching and Research section at Wuzhou University. Welcome you to this mini lecture. Today we will cover Chapter 2, Section 1, the time domain description of basic continuous time signals. First, let's discuss typical basic signals. Typical basic signals fall into 5 categories: the sine signal, the real exponential signal, the imaginary exponential signal, the complex exponential signal, and the sampling function. The first signal is a functional expression of the sine signal f of t equals a sine omega 0 times t plus phi. The corresponding waveform is shown in the figure below. Here, a denotes the amplitude, omega 0 denotes the angular frequency in radians per second, and phi denotes the initial phase in radians. As a fundamental periodic signal, the sine signal is widely used in multiple fields, such as communication systems, electric power and control systems, and signal processing and measurement. The second signal is the real exponential signal. Its functional expression is f of t equals a e raised to the power of alpha t. A represents the initial value of a signal, which determines its magnitude at t equals 0. When alpha greater than 0, the function increases monotonically, and when alpha less than 0, it decreases monotonically. The waveform is as shown in the figure. In short, the characteristics of a real exponential signal mainly depend on the sign of alpha, which determines whether the signal grows or decays, whereas it determines the initial amplitude of the signal. Real exponential signals are widely used in circuit analysis, wireless communications, radar systems, and industrial control, among other areas. The third signal is the imaginary exponential signal. Its functional expression is f of t equals e raised to the power of j omega 0 times t. According to Euler's formula, trigonometric signals can be represented using imaginary exponential signals. The formulas are as follows. To determine the period of an imaginary exponential signal, set up the condition as f of t equals f of t plus t, expressed using the imaginary exponential signal. E raised to the power of j omega 0 t equals e raised to the power of j omega 0, open parenthesis, t plus t, close parenthesis. And this shows that the function values at t and t plus t are equal, i.e., the signal is periodic. From this relationship, omega 0 times t equals 2 pi times n, it follows that the period is an integer multiple of 2 pi, where n is an integer. The fundamental period of the imaginary exponential signal is t0 equals 2 pi divided by omega 0. In signal processing, imaginary exponential signals are commonly used to represent harmonic components, and their periodicity and frequency characteristics are crucial for spectrum analysis. The fourth signal is the complex exponential signal. Its expression is f of t equals a e raised to the power of st, whereas is a complex number equal to sigma plus j asterisk omega 0. Substitute s into f of t. The resulting expression is f of t equals a e raised to the power of sigma t times e raised to the power of j omega 0 times t. Earlier we studied the imaginary exponential signal. Decompose the imaginary exponential signal into cosine of omega 0 times t plus j sine of omega 0 times t. Substitute into the equation, and finally obtain the expression of f of t as a e raised to the power of sigma t cosine of omega 0 times t plus j 8 e raised to the power of sigma t sine of omega 0 times t. In this expression, the following terms represent the components of the signal. The real part is a e raised to the power of sigma t cosine of omega 0 times t, which represents the cosine component. The imaginary part is j a e raised to the power of sigma t sine of omega 0 times t, which represents the sine component. The waveform corresponding to a negative exponential is shown in the figure. The characteristics of the signal are: when sigma is greater than 0, the signal grows with time. When sigma is smaller than 0, the signal decays with time. The complex exponential signal is fundamental in signal processing and is widely used in communications and control systems. The fifth signal is the sampling function. This function will be quite important in later study. SA of t equals sine of t divided by t. The sampling function has the following key properties. The first is special point values. Sin 0 is equal to 1. By inspecting the plot of this function, you can see that when t equals 0, the function value is 1. Sin k pi equals 0, where k equals plus or minus 1, plus or minus 2, and other integers. The second is an integral property over the entire real line. The integral saw from minus infinity to plus infinity equals pi. The third key property is a closely related function of saw of t, namely sinc of t, which is defined as sinc of t equals sine of open parenthesis pi t close parenthesis divided by open parenthesis pi t close parenthesis. These properties make the sampling function widely applicable in fields such as signal processing. The second part concerns singular signals. A singular signal is a signal whose function itself or whose derivative/integral has points of discontinuity, jump discontinuities, also called an abrupt signal. It plays a key role in physical system modeling, fault diagnosis, and signal processing. We will primarily introduce the following four typical signals: the unit step signal, the impulse signal, the ramp signal, and the impulse doublet. First, we explain the unit step signal. Its functional expression is as shown: u of t equals 1 when t greater than 0, and equals 0 when t less than 0. The waveform is as shown above. When the unit step signal is shifted, its functional expression is as shown: when t greater than t0, the function value equals 1. When t less than t0, the function value equals 0. The corresponding waveform is shown below. Next, we introduce the roles of the step signal. First, it can be used to represent an arbitrary square wave pulse signal. For example, f of t equals u of t minus capital T minus u of t minus 2t. Figure A plots the two signals u of t minus capital T and negative u of t minus 2t. Adding these two signals yields a final square wave pulse signal, as shown in Figure B. The second role of the step signal is to use its one-sidedness to indicate the time range of a signal. Take the sine signal just mentioned as an example. The domain of the sine signal is from minus infinity to plus infinity. In the figure, multiply the sine signal by the step signal. When t greater than 0, the step signal equals 1. When t less than 0, it equals 0. In this way, we extract the portion of the signal from 0 to plus infinity, as shown in Figure A. Figure B shifts the sine signal, sine of omega 0 times t, by t0, to obtain the resulting signal, sine of omega 0 times open parenthesis t minus t0 close parenthesis. Here we assume t0 greater than 0. Multiplying this signal by a step signal finally extracts the time segment t greater than 0, as shown in Figure B. Figure C performs the following operation to sine of omega 0 times t, u of t minus t0, with the default assumption that t0 greater than 0. When t greater than t0, the function value is 1, otherwise it is 0. Retaining the portion from t0 plus infinity yields Figure C. Figure D shows the sine signal shifted to the right by t0 units, then multiplied by u of t minus t0. This retains a portion from t0 to plus infinity, as shown in figure D. To summarize, observe the middle portion of the step signal and make it greater than 0. This yields a range of t. Within this range, the function value is 1. Outside this range, the function value is 0. This represents the time range of the signal. Typically, the unit step signal is used to describe instantaneous switching behavior, such as a circuit being connected to a power supply. The second signal is the impulse signal. First, we introduce the limiting model of the impulse signal. The impulse signal delta of t can be obtained by letting the width delta of a rectangular pulse signal f_delta t or triangular pulse signal g_delta of t tend to 0. We can first draw a rectangle spanning from minus delta to plus delta on the horizontal axis with height 1 over 2 delta, or draw a triangle spanning from minus delta to plus delta with height 1 over delta, ensuring that the total area of this rectangle or triangle is 1. As delta tends to 0, it approaches the origin arbitrarily closely. At that point, what we obtain is an impulse signal of height 1. Its integral over the range from minus infinity to plus infinity equals 1, which reflects the special property of the impulse signal. Next, we introduce the properties of the impulse signal. First, the shifting property. F of t delta of t minus t0 equals f of t0 delta of t minus t0. Delta of t minus t0 indicates that the signal is concentrated only at t0. F of t0 multiplied by delta of t minus t0 represents filtering out the function value of f at t0 and multiplied by delta of t minus t0, which means the impulse signal can sift out the value of a function at a specific instant. Second, the sampling property. Integrating f of t times delta of t minus t0 from minus infinity to plus infinity yields a value of the function at t equals t0, namely f of t0. This indicates that an impulse signal can be used as a sampling tool in signal processing, capable of extracting the exact value of a function at a specific moment. The third property is the scaling property. Delta of a times t equals 1 divided by the absolute value of a times delta of t. Here is the scaling factor. When the time axis is scaled, the amplitude of the delta function is adjusted by the factor 1 divided by the absolute value of a to preserve the normalization condition. This property reflects the stability of the delta function under time transformations and is important in signal processing and mathematical analysis. Next, we discuss the relationship between the impulse signal and the step signal. The integral of the impulse signal delta of t from minus infinity to t equals the step signal u of t. The step signal u of t equals 1 when t greater than 0 and equals 0 when t less than 0. The derivative of the step signal u of t equals the impulse signal delta of t. The figures respectively show the waveforms of u of t and delta of t, intuitively illustrating their time domain characteristics. The third singular signal is the ramped signal r of t when t greater than or equal to 0. Its value is t, and when t less than 0 it is 0. The waveform is as shown in the figure. Its relationship with the step signal is the integral of the step signal yields the ramp signal. The derivative of the ramp signal yields the step signal. The fourth signal is the impulse doublet. The derivative of the impulse signal is the impulse doublet. The impulse doublet has two properties. One property is that its integral over the entire real line is 0, i.e., the integral from negative infinity to positive infinity of delta prime of t with respect to t equals 0. The second property is an integral transform property. The integral from negative infinity to some time t equals the impulse at that time, i.e., the integral from negative infinity to t of delta prime of tau with respect to tau equals delta of t. The waveform of the impulse doublet is as shown in the figure on the right. In the figure, the behavior at t equals 0 reflects the instantaneous change characteristic of the impulse doublet. Finally, we summarize the calculus relationships among the four singular signals. First, the impulse doublet equals the derivative of the impulse signal. The impulse signal equals the integral of the impulse doublet. The impulse signal equals the derivative of the step signal. And the step signal equals the integral of the impulse signal from minus infinity to t. The step signal equals the derivative of the ramp signal. And the ramp signal equals the integral of the step signal from minus infinity to t. Finally, please reflect on this lesson and complete the following problems as homework, with the aim of consolidating the knowledge points learned today and further deepening your understanding. This concludes this mini lecture. See you in the next class.